In this example, we are going to take a look at several functions and determine if they are even, odd, or neither. Before we begin, let's review what does it mean for a function to be even, odd, or neither. So to be an even function, that means for all x, so all of the inputs that you could use in the domain of the function, if we take a look at the negative values of those inputs, we end up with the same outputs that we did with the original function. Another way you can test if a function is even is by taking a look at the graph and seeing what type of symmetry you have. For a function to be even, because the positive inputs and the negative inputs give equivalent outputs, you have symmetry about the y-axis. So that means if you were to use the y-axis as your folding line, you would end up with two identical copies on top of each other. An odd function is defined similarly, but this time if we take a look at the function values when we use the opposite inputs, we now get the opposite outputs. The type of symmetry that we have in this case is symmetry about the origin. And this one sometimes is a bit hard to think about. Instead of folding, you can think about rotate 180 degrees. And if you end up with the same picture, then that means the function is odd. A function is neither even or odd if it's neither one. So you're either even, odd, or neither. There's no other option. So let's start with the first one, y equals 6x squared. So let's consider what happens if we replace x with negative x. What happens if you square a negative number? It becomes positive. So we will get the same outputs as we did for the original function. If you want to use the function notation here, we could rewrite this as f of x equals 6x squared. And we've just shown that f of negative x is equal to f of x. So this function is even. We can take a look at the graph and verify looking at the symmetry as well. So I'm going to jump over to Desmos and plug in this function. So here I am in the Desmos graphing calculator. I have my function y equals 6x squared. So we have a nice parabola starting from the origin 0, 0. So if I imagine taking the y-axis as my fold line, I do see that those two sides of the parabola would line up perfectly with one another. So this also verifies that this function is indeed even. Let's take a look at part B. Here we're working with a trig function, y equals sine of x. So let's consider writing this in function notation, just so we can match that up with our definition. So if we take a look at f of negative x, we're wondering what is that equal to? So to help us check some of the values, I'm going to pull up a unit circle and see what happens when we use the opposite inputs. Recall on the unit circle that for any given angle that is marked on the unit circle, the ordered pair associated with it is given in the format cosine of x, sine of x. So when I look at my unit circle, I'm focusing on all of the second coordinates because we're talking about the function sine of x. So let's look at an example of using a positive x value. So sine of, let's say, 30 degrees. So that's in quadrant 1. So the sine value of 30 degrees, looking at the second coordinate, is positive 1/2. Now, what happens if I look at sine of negative 30? So now I would need to go in a clockwise clockwise rotation, so starting at the positive x-axis at 1, 0, if I rotate 30 degrees going in the opposite direction, that indicates a negative rotation. That's the same thing as positive 330. When I look at the sign value there, it's negative 1/2. So my two function values are indeed opposite. And I could go through and do many more examples using, a positive angle and then the negative, but this is going to hold true for any example that you could look at. So in this example, when we look at the opposite inputs, we do get the opposite outputs of what we had before. So our sine function is odd. In fact, sine and its reciprocal cosecant, and also tangent and cotangent, all of those 4 trig functions are odd. The only 2 that are even are cosine and secant. Let's verify with the graph of sine of x that it is indeed odd. So again, if you imagine taking the curve and rotating it 180 degrees, the right-hand section, so think about starting at 0, 0, the right-hand section would end up perfectly on the left, and the left section would end up falling perfectly on the right. We can also see this by looking at the function sine of negative x, and we see that they are in fact opposites. So that also verifies that our function is indeed odd. All right, last one. Y equals the 4th root of x. Let's use function notation and consider what happens when we plug in the opposite input. Well, that would look like the 4th root of negative x. There's something funny that happens when we try to take the even root of a negative number. As an example, if I tried to take the 4th root of, let's say, negative 16. Now, some may be tempted to say, well, that's negative 2, because if you raise negative 2 to the 4th power, you end up with 16. However, because it's even, it's going to end up being positive 16. So I actually can't use any negative values. So this definitely is not going to be true that f of negative x is equal to f of x or negative f of x. I can't even plug it in. So this function should be neither even or odd because it does not fulfill either definition. Let's take a look at the graph to see that we, in fact, do not have either of the symmetries that we were talking about. And I'm going to plug in a power of 1/4 to help me graph this more quickly. So we see the function curves out from 0, 0. So there's not even a section of the graph on the left to match up with. So it's definitely not even. And in order to be odd, we would have to have the same curve coming down here in quadrant 3, which we don't have. So it's not odd as well. So it's neither even or odd.